So hello everyone, I am Ashutosh Mehra and I have been part of J9 VM team and now OpenJ9 project. I'm working with OpenJ9 project as a contributor, and last year we added a feature related to idle tuning in OpenJ9. So basically we try to reduce the memory footprint of OpenJ9 when the application is in idle state. So why do we need to do this? Why do we need to tune OpenJ9 during idle phase? The reason or the use case comes from the cloud environment, which is being used for deploying applications these days. So different cloud vendors have different pricing models, and if your cloud vendor is using consumption-based pricing model and using memory as the resource for charging you, as an example, like how much memory you are consuming in a day or per hour, if that's the criteria for charging, then obviously you would need your application's memory footprint to be as low as possible, and you would want it to be low not only during active cycle when your application is servicing the request, but also when there's no load on the application. So with this context, what action the JVM needs to take? In JVM, we know that heap is the largest consumer of memory. So I have depicted the heap state during active and idle cycle in this slide. So on the left hand side is the active, the heap state in the active state in the active phase. So you have
Ashley, we're still seeing the title slide.
Okay, I'll wait for a few seconds. I have moved to second slide.
We're seeing the whole. There we go.
Okay, so is it moving now?
Yeah, thanks, Ashu.
Okay. So yeah, so in this slide, I'm depicting the heap state during active and idle cycle. So during active state, you can see there's XMX value, which is your maximum size your heap can expand up to. So at any given point in time, your JVM would have reserved some amount of space. Reserve means this much heap memory is actually backed by a physical page. So then there's then your JVM at any point in time will be using some amount of heap memory for allocating objects. That is indicated by the green bar, which indicates the current usage of your application. So now if your application goes from active state to idle, say it has completed some transactions in the active state, and now there is no load on the application, it goes into idle state. So in the idle state, you will find that many of the objects have become garbage. There are no references to those objects. They were used during the transactions earlier, but are not anymore live. So there is a certain section of the heap which has turned into garbage, but the JVM is not collecting that memory because it doesn't have any memory pressure to run a GC cycle. So that garbage sits in your heap and keeps your memory footprint bloated. If you can collect that garbage and decommit the memory. Decommit means return the memory back to the OS. That's the state which is indicated in the last diagram, which has the heading of idle tuning. You can see the large part of the heap we are able to decommit if we do a GC cycle. So that will also reduce the memory footprint of your application. So this is the tuning that we have done in OpenJ9. So coming to OpenJ9 implementation, there are two steps to idle tuning. The first is identifying the idle state of your application. So OpenJ9 already had a notion of idleness, idle state, thanks to the JIT sampler thread. So the sampler thread is a native thread which samples the JVM at a predetermined frequency. It collects some statistics related to CPU consumption, memory, class loading state, JIT state. Along with that, it also determines whether there are any active threads or not. And based on this based on the active threads, it changes its state. So the flowchart you're seeing on the slide shows a very simple view of how the sampler thread states change. So it starts in the default state, which is nothing but an active state. During this state, it sets its frequency or the sampling frequency to 10 milliseconds. That means it wakes up every 10 milliseconds, performs some, collects some samples, determines whether there are any active threads or not, and then goes back to sleep. So in active state, if it detects there is no activity, there are no active threads for 5 seconds, then it changes state to idle. In idle state, it also changes its sampling frequency to 1 second. Since the application is idle, it doesn't make sense to sample the application that frequently. So it increases the sampling frequency to 1 second. If it continues in idle state for another 50 seconds, then it changes state to deep idle. And in deep idle, the sampling frequency is set to 100 seconds. So to determine whether the VM has gone into idle or not, we rely on JIT sampler's state logic, and we say that if sampler thread continues to be in deep idle for some specific amount of time, then we declare the VM as idle. So at that time, the sampler thread will send a notification to the idle to the VM to change its state to idle state. Now, the amount of time that the VM can wait to declare itself as idle can be configured using -XX colon idle tuning min idle wait time option. Now, since we are relying on relying on sampler thread state logic to declare VM as idle, it has two implications. Uh, First is you can see from the flowchart, it takes around 55 seconds for the sampler thread to go into deep idle, and unless the sampler thread has gone into deep idle, we don't declare the VM as idle. So to declare VM as idle, it will take minimum of 55 seconds. And second implication is since we are tied to sampler thread state logic, and sampler thread has to send a notification to a VM. That means the VM can be declared idle only at discrete points in time. This is because when sampler thread is in deep idle, it wakes up every 100 seconds. So once it goes once when it wakes up at that point, only it can declare the VM as idle if the min idle wait time has elapsed at that particular point. So this is in short about the logic that we use for identifying the idle state of the VM. If you want to know whether your VM has gone into idle state or not, you can actually enable JIT logs. So to enable JIT logs, you can use -x JIT colon verbose with compile performance as the sub option. This JIT logs will contain a lot of compilation related information, which methods are being compiled and all. In addition to that, this particular option also causes sampler thread to emit messages when it changes its state. So I have put up a snippet of the JIT logs for an application which has gone into idle state. So you can see the first message, which is in red font. It says that the sampling thread has gone into idle state and its frequency has changed to 1 second. That happened at t equals to 17 seconds. So the time given time in front of t is in milliseconds. So if you convert it, it comes to around 17 seconds. Followed that, there are a couple of compilation related information, and after that, at time 67 second, you see that there are two messages. So the sampling thread has actually changed its state to deep idle, and at the same time it also notified the VM to change its state to idle. So that number 2 indicates that the VM state has been changed to idle. So in a sense, if you want to determine whether your VM is running in idle state or not, you can enable JIT logs and look for this particular statement sampling thread changed VM state to 2. So once the VM has gone into idle, now it has to take action to reduce its heap, reduce its heap memory, that is decommit the heap memory. And that behavior is governed by two options. The first is -x colon idle tuning GC on idle, and the other is compact on idle. So in both cases, the VM will optionally do a GC when it gets a notification from the sampler thread that it has gone into idle state. So at that time, it may do a GC, and then it will decommit the free pages in the heap. So the condition that governs whether JVM will do a GC or not is actually depends on amount of memory that has been allocated in tenure space since the last GC cycle. So in in 0.9 release of OpenJ9, this value is actually 40%. That means if 40% of the tenure heap memory has been allocated since last GC, the JVM will trigger a GC cycle when it goes into idle phase. And after completing the GC, it will decommit the freed heap memory. This is likely to change in the future release, as there is some discussion on whether to enable GC unconditionally or not. The difference between compact on idle and GC on idle is that that in compact on idle, the JVM will do GC as well as compaction. So there is likely more memory available to decommit because of compaction. Now these two options, you can check the behavior of these two options in GC logs. So if you enable GC logs using -verbose :GC or -x verbose GC log, and the JVM performs a GC during idle phase, you will see a GC cycle which has a reason equals to VM idle. So if you observe in GC logs, there is a GC cycle which has the reason as VM idle. That particular GC cycle has happened in idle phase. And similarly, when JVM decommits memory, it emits a heap resize tag in the GC log, which has type as release free pages and reason as idle. This tag also has a field called amount, which is supposed to indicate how much memory has been decommitted. But this information is currently inaccurate because we are not keeping track of which free pages are actually backed by physical page or not. So this information is not correct. If we want to observe, if we want to measure how much memory footprint has gone down due to idle tuning, then I would suggest to observe the resident set size of your process. On Linux, we can do that using top. So if the resident memory of your process goes down, then it should go down during this idle tuning when the heap resize message is emitted in the GC log. During that time, you should observe your resident memory going down. So yeah, that covers the OpenJ9 implementation. The next slide talks about the options related to idle tuning, which most of them I've already covered. The only one which I've mentioned is idle tuning min free heap. This option tells the JVM how much percentage of memory it should not decommit out of the free heap. So if you set min free heap on idle to say 20, that would mean out of total free heap available, to decommit, it will not decommit 20% of the memory of the free heap. So 80% of it will be decommitted. As of now, the default value is 0. That means it decommits everything. And from Java 9 onwards, we have enabled GC on idle with Xtune virtualized. So if you set Xtune virtualized, which we generally recommend for cloud deployments, then GC on idle will get enabled by default. Few more points related to idle tuning. First of all, it is supported only on GenCon policy as of now. And in GenCon also, we are actually decommitting memory only on the tenure space. So GenCon has two memory spaces, nursery space and tenure. Tenure is the one which corresponds to long living objects, and that's the one which we decommit during idle phase. We enabled this annual support for idle tuning on Linux x86 initially, but this year we have also enabled it on Linux, on all supported Linux platforms, P, Power, Intel, and Z Linux, and also enabled it on ZOS. And with the 0.9 release of OpenJ9, the Docker images which we can obtain from hub.docker.com under adopt OpenJDK, the idle tuning options are already set. So you don't need to set these idle tuning options specifically if you are using Docker images. I think that's all I have.
Thanks, Ashu. Does anybody have any questions? So I have one. Ashu, why do we only decommit from tenure?
So I'm not sure of the actual reason why we actually did it. I'm not aware of that, but all I can think of at this moment is probably nursery space, something which is very active, since most of the allocations happen during nursery in the nursery region, and if we decommit from the nursery region, and when the application comes back into active state, it will suffer more page faults. So when we move back to active state, it may likely impact the performance a bit. That's the only thing that I can think of at this moment.
Okay, that makes sense.